Alright, so let's wrap up the chapter with the theorem, which is probably the last theorem we're going to see in this class. So this is called the Cayley-Hamilton theorem. Alright, so suppose A is an n by n matrix, and P lambda is the characteristic polynomial of A. So let's write it out. So the leading coefficient is -1 to the n plus Cn minus 1 lambda n minus 1. It's all the way to C2 lambda squared plus C1 lambda plus C0. So this is the characteristic polynomial of A. So if we try to replace lambda by A, which is a little weird because lambda is a number, but A is a matrix, but mostly can be done because we know how to calculate A to the n because A is a square matrix. So replace all the powers of lambda by the powers of A, and lambda square is A square, and C1 lambda is A. And because these are matrices, so we can't really just have a constant here. So instead of a constant, we have the identity matrix here. Then the conclusion is if we replace lambda by the matrix A, the right-hand side is equal to 0. Let's be clear, this is the 0 matrix. Okay. So let's do a proof just for a special case. So let's do the proof for the case where n equal to 3 and A is diagonalizable. Okay, so suppose n is equal to 3, so A is a 3 by 3 matrix, and it's to assume A is diagonalizable. So because A is diagonalizable, we know that A is equal to P D P inverse, where D is the diagonal matrix, with diagonals being the eigenvalues. Okay. All right, so let's plug in A into the characteristic polynomial. So P of A is equal to -1 cubed, which is just -1, negative A cubed, plus C plus C2A squared, plus C1A plus C0 times the identity matrix. But we know, because A can be diagonalized, then A cubed is just PDP inverse, PD cube, P inverse, plus C2 times A squared, which is PD squared, P inverse, and plus C1, PDP inverse, plus C0. Okay, so we're going to use a trick here. We're going to use the fact that the identity matrix is technically P times P inverse. The reason we do this is because now you realize we can just all the 4 terms have P in the front and P inverse in the back, so we can factor them out. So this is equal to P times negative D cubed plus C2D squared plus C1D plus C0 times P inverse. Okay, so there's no more P's involved in this. So P and P inverse stay there. But we know D cube is just lambda 1 cube, lambda 2 cube, lambda 3 cube. And this is going to take more space. C2, D square is lambda 1 square, lambda 2 square, lambda 3 square. And D is lambda 1, lambda 2, lambda 3. Oh, I forgot I here. This is very important. There's an I here. So C0 times I, which is 1, 1, 1, times P inverse. So this is equal to P times, if we combine all the entries, then the new thing is the diagonal entry. The top left is minus lambda 1 cube plus C2 lambda 1 square plus C1 lambda plus C0. The middle one is same thing but with lambda 2. C1 plus C0 and lambda cube, lambda 3 C1 lambda. C1 lambda 3 plus C0. So it's a diagonal matrix with diagonal entries being these things. But remember these coefficients coming from the characteristic polynomial. So these diagonal entries are literally P of lambda 1, P of lambda 2, P of lambda 3, and times P inverse. But let's recall that P of these terms are all 0. These are 0 because lambda 1, lambda 2, lambda 3 are roots of the characteristic equation. P lambda equal to 0. So all these diagonal entries are actually equal to 0. So this is equal to P times a 0 entry, 0 matrix times P inverse, which gives you 0. And this is our proof. Okay, so why is this theorem useful? So this theorem can be useful. So Cayley-Hamilton theorem provides an alternative method to calculate a to the kth power. Okay, so let's do a small example. So let's take a equals to 3, negative 2, 1, 0. So the characteristic polynomial is determinant of a minus lambda I equal to 0, which means determinant of 3 minus lambda, negative 2, 1, 0 minus lambda equal to 0, which gives you 3 minus lambda times negative lambda minus negative 2 times 1 equal to 0. This gives you lambda squared minus 3 lambda plus 2 equal to 0. Notice that we're going to stop here. We're not going to solve for eigenvectors. So this is the characteristic polynomial. By the theorem, this tells you a squared minus 3a plus 2 times the identity matrix equal to the 0 matrix. Well, this allows us to calculate a squared because this tells you that a squared is 3a minus 2i. We don't really need to do any matrix multiplication. 3a is 9, negative 6, 3, 0. 2i is 2, 0, 0, 2. So this gives you 7, negative 6, 3, negative 2. So here we calculated a square without using matrix multiplication. And this can be generalized. So this, if you multiply it by a on both sides, then we get a cubed minus 3a squared plus 2a equal to 0, which tells you that a cubed is 3a squared minus 2a. And a squared is here, a is here, so we can still calculate all these things without matrix multiplication. So 3a squared is 21, negative 18, 9, negative 6 minus 2a, which is 6, negative 4, 2, 0. This is 15, negative 14, 7, negative 6. And so on, so forth. So on, so forth. Fourth. So a to the fourth can be calculated by using a to the third and a squared. And a to the fifth is 3a to the fourth minus 2a cubed, so on, so forth. So we can calculate all powers of a without actually multiplying matrices together. That's not it. Let's take this. If we multiply by a inverse, then we get a minus 3i plus 2a inverse equal to 0. This tells you that 2a inverse equals to 3i minus a. So A inverse is 3/2 I minus 1/2 A. And so this is equal to 3/2 times 3/2 I is 3/2, 3/2, 0, 0. And minus, where's my A? A is 3, negative 2, 1, 0. And divided by 2. So 3/2, negative 1, 1/2, 0. So this is equal to 0, 1, negative 1/2, 3/2. So we can also use the Cayley-Hamilton theorem to calculate A inverse without calculating any matrix multiplication. So, yep. So the Cayley-Hamilton theorem allows you to calculate h to the k, and this is for both positive or negative integers. All right, so that's it for chapter 6.